Along in this lecture we find out the distance between the centers of two circles. In the drawing we have rectangle ABCD. We know that side AB of this rectangle equals to 7 units, side BC equals to 24 units. Inside this rectangle ABCD we have those two circles. The center of this circle is here at point Q, the center of this circle is here at point P. And our mission is to find out the distance between the centers of those two circles. That is to say, our mission is to find out the length of this line segment QP. So first of all, because of the fact that ABCD is a rectangle, it means that all of those four angles must be right angles. So write it down. This angle must be equal to 90 degrees. This angle must be also equal to 90 degrees in its size. This angle must be equal to 90 degrees. And finally, this angle must be also equal to 90 degrees. In addition, because of the fact that ABCD is a rectangle, we know that the opposite sides of a rectangle are equal to each other. That is to say, side AB equals to side DC, but AB is 7, therefore DC must be also equal to 7 units. Likewise, according to the sum rule, side BC must be equal to side AD, but BC is 24, therefore AD must be also equal to 24 units in its length. In the next step, we will focus on the right triangle ABC, and we will implement the Pythagoras theorem in this right triangle ABC. Okay, so according to the Pythagoras theorem, in the right triangle ABC, by PT is a relation from Pythagoras theorem. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So, the hypotenuse in the right triangle ABC is AC, therefore the square of the hypotenuse is AC squared. And it must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to AB squared plus BC squared. Repeat again. According to the Pythagoras theorem, in the right triangle ABC, AC squared equals to AB squared plus BC squared. By PT is the relation from Pythagoras theorem. So AC squared, that is the square of the hypotenuse, equals to AB squared. AB is 7, therefore AB squared is 7 squared, that is 49, plus BC squared. BC is 24, therefore BC squared is 24 squared, that is 576. So in total we found out that AC squared equals to 49 plus 576 is 625. AC squared equals to 625. We take a root out of this equation and finally we get that AC equals to the square root of 625, that is actually 25. So the length of the hypotenuse AC of the right triangle ABC is equals to 25 units. So right here, the hypotenuse AC of the right triangle ABC equals to 25 units in its length. So here, the right triangle ABC blocks this circle, and the right triangle ADC blocks this circle. So those two circles, each of them is blocked by a right triangle. Therefore, we'll find a general formula for any circle that is blocked a right triangle. That is to say, we find a formula that will help us to find out the radius of any circle that is blocked by a right triangle only by knowing the side lengths of the right triangle that blocks the circle. Okay, so actually here we have the right triangle, triangle ABC. This right triangle ABC blocks this circle, and we know that the radius of this circle equals to x. Now we're trying to develop a formula that will help us to find out the radius of this circle x only by knowing the side lengths of this right triangle ABC that blocks this circle. We define the point of tendency of tangent BC with this circle Sn. The radius ON is known to point N, that is the point of tendency of tangent BC with this circle, and whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius NO. That is to say, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. The center of this circle is here at point O, and the radius OM, that is R, is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. That is to say, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule number 1. So actually we can implement rule number 1 in our drawing. We define the point of tendency of tangent AB with this circle as M. We join points O and M together by straight line. OM is the radius of this circle that is equal to x. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. That is to say, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. So inside quadrilateral M, B, and O, we have 1, 2 right angles, therefore the fourth angle must be also equal to 90 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So inside quadrilateral OM, BN, we have 4 right angles. Therefore, can relate to this quadrilateral OMBN as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, NO equals to BM. But NO is x, therefore MB must be also equal to x. Likewise, according to the same rule, in rectangle OMBN, side OM must be equal to the opposite side NB. But OM is x, therefore NB must be also equal to x. So we actually found out that this rectangle this quadrilateral MOBN is not a rectangle but a square. Why? Because of the fact that all of its sides are equal to each other. Each side of this quadrilateral is equal to x. Therefore, this quadrilateral MOBN is a square. Okay, what is the length of AM? From the drawings it's very easy to see that AM equals to AB minus BM. Again, AB minus BM equals to AM. So AM equals to AB, that is A, minus BM, that is X. So in total, AM equals to A minus X. So we can write here that AM equals to A minus x. Likewise, we find out the length of this line segment Cn. From doing it, it's very easy to see that Cn equals to Cb minus Nb. Again, Cb is b and Nb is x, therefore in total Cn equals to b minus x. So can I tell that Cn equals to b minus x? So in conclusion, we found out that Nc equals to b minus x, while Am equals to a minus x. Then we have here rule number 2. According to rule number 2, the lengths of two tangents from a common standpoint to a circle are equal. We have the common standpoint point P. From the common standpoint point P, we have two tangents to the circle, tangent PA and tangent PB. And according to this rule number 2, they are equal to each other. That is to say, PA equals to PB. So we can implement rule number 2 in our drawing. Well, because in our drawing we have the common standpoint point A. We define the point of tendency of tangent AC with this circle as point S. So from the common standpoint point A, we have two tangents to this circle, tangent AM and tangent AS. And according to rule number 2, they are equal to each other. That is to say, AM equals to AS, but AM is A minus X, therefore AS must be also equal to A minus X. Likewise, according to the same rule, if you focus on the common standpoint point C, from the common standpoint point C, we have two tangents to the circle, tangent CN and tangent CS. And according to rule number 2, they are equal to each other. That is to say, CN equals to CS. But Cn is b minus x, therefore Cs must be also equal to b minus x. Okay, so the hypotenuse AC AC of this right triangle ABC, according to our definition, it is equal to 3 units in its length. So the hypotenuse AC equals to 3 from one side, but from the other side, the hypotenuse AC in total equals to AS plus SC. It is AS plus SC. So C equals to AS, that is A minus X, plus SC, that is B minus X. So in total, the length of the hypotenuse AC, that is C, is equals to A plus B minus X is minus 2X. C equals to A plus B minus 2X. We add 2X to this equation, and we get that C plus 2X equals to A plus B. We subtract 3 from this equation, and we get that 2X equals to A plus 2x equals to A plus B minus C. We divide this equation by 2 and finally we get that x equals to A plus B minus C over 2. So actually we succeeded to develop a general formula for the radius of any circle that is blocked by a right triangle. The radius of this circle X that is blocked by the right triangle ABC equals to A plus B minus C over 2. Again, the radius of this circle X that is blocked by the right triangle ABC equals to A plus B minus C over 2. Now we can implement the new formula in order to find out the radius of this circle that is blocked by the right triangle ABC. We will define the radius of this circle as R. The radius of this circle equals to R according to our definition. So according to the new formula, the radius R of this circle that is blocked by the right triangle ABC, must be equal to AB plus BC minus AC over 2. Repeat again. The radius of this circle that is equal to R, and it is blocked by the right triangle ABC, according to the new formula, must be equal to AB plus BC minus AC over 2. AB is 7 plus BC, that is 24, minus AC, that is 25 over 2. So 7 plus 24 is 31, and 31 minus 25 over 2. 31 minus 25 is 6, and 6 over 2 is 3. So finally we found out that the radius of this circle R equals to 3 units. Likewise, we find out the radius of this circle that is blocked by the right triangle ADC. We define the radius of this circle as x. According to the new formula, the radius of this circle x that is blocked by the right triangle ADC, it must be equal to, the radius x must be equal to CD plus DA minus CA over 2. Repeat again, the radius of this circle x that is blocked by the right triangle ADC must be equal to CD, that is 7, plus DA, that is 24, minus CA, that is 25 over 2. 7 plus 24 is 31, 31 minus 25 is 6, and 6 over 2 is 3. So we found out that x also equals to 3 units in its length. The radius of this circle x also equals to 3 units in its length. We define the point of tendency of tangent BC with this circle as M. So PM is the radius of this circle. The radius PM is drawn to point M, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius MP. If BC is perpendicular to MP, we get that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. Likewise, we define the point of tendency of tangent AB with this circle as N. We join points P and N together by a straight line. Pn is the radius of this circle that is equal to 3 units. The radius Pn is drawn to point N, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NP. That is to say, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. So inside quadrilateral PNBM, we have 1, 2 third angles, therefore the fourth angle must be also equal to 90 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So inside quadrilateral PNBM, we have 4 angles, therefore can relate to this quadrilateral PNBM as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other, that is to say PN equals to BM. But Pn is 3, therefore Bm must be also equal to 3. Likewise, according to the same rule, in rectangle PN, Pm must be equal to Nb. But Pm is 3, therefore Nb must be also equal to 3 units in its length. So we actually found out that this quadrilateral NPBM is not a rectangle but a square. Why? Because of the fact that all of its sides are equal to each other. Each side of this square is equal to 3 units. We repeat on the same process on this circle, and we will create here another square with one side that is equal to 3 units. So those two squares will be two identical squares. Here we define the point of tendency of tangent dA with this circle as G. So here we have the radius QG that is drawn to point G, that is the point of tendency of tangent AD with this circle. Whenever you have a radius that is drawn to the point of tendency, then tangent AD will be perpendicular to the radius GQ. That is to say, this angle equals to 90 degrees, and this angle also equal to 90 degrees according to rule number 1. We define the point of tendency of tangent CD with this circle as K. We join points Q and K together by straight line. QK is the radius of this circle that is equal to 3 units. The radius QK is drawn to point K, that is the point of tendency of tangent CD with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent CD will be perpendicular to the radius KQ. If CD is perpendicular to KQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. So inside quadrangle QK DG we have 3 angles, therefore the fourth angle must be equal to 90 degrees. Therefore can relate to this quadrangle QK DG is a rectangle, and we also know that the opposite sides of a rectangle are equal to each other. That is to say KQ equals to DG. But KQ is 3, therefore DG must be also equal to 3 units in its length. Likewise, according to the same rule, in the same rectangle QKDG, QG must be equal to KD. But QG is 3, therefore KD must be also equal to 3 units in its length. Again, here we found out that quadrangle QKDG is not a rectangle, but a square. Why? Because all of its sides are equal to each other. Each side of this square is equal to 3 units in its length. In the next step, we'll extend the radius GQ of this circle by straight line until it touches side BC of this rectangle ABCD. And we will define the touching point of the extended radius GQ and side BC as T. The radius of any circle, it is absolutely a straight line. When you extend a straight line by straight line, the result is a straight line, therefore GT is one straight line. Inside the big quadrangle GDTC, we have 1, 2, 3 angles, therefore the fourth angle must be also equal to 90 degrees, according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. So inside this quadrangle TCDG we have 4 angles, therefore we can relate to this big quadrangle TCDG as a rectangle. And we also know that the opposite sides of this rectangle must be equal to each other. That is to say GD equals to TC. But GD is 3, therefore TC must be also equal to 3. Likewise, according to the same rule, in the big rectangle TCDG, side DC must be equal to side GT. But DC is 7, therefore GT must be also equal to 7 units in its length. GT equals to 7. This side GT equals to 7 units in its length. In the next step, we will extend the radius NP of this circle by straight line until it touches side DC of rectangle ABCD. We will define the touching point of the extended radius NP inside DC of the rectangle as point Y, and we'll focus again when you extend the straight line by straight line, the result is a straight line, therefore NY is a straight line. In the next step we'll focus on the big quadrilateral NBCY. Inside this big quadrilateral we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. So we can relate to this quadrilateral NYCB with 4 right angles as a rectangle. And we also note that the opposite sides of this rectangle must be equal to each other. That is to say NB equals to YC. But NB is 3, therefore YC must be also equal to 3 units in its length. Likewise, according to the same rule, in the same rectangle, BC equals to NY. But BC is 24, therefore NY must be also equal to 24 units in its length. NY equals to 24 units in its length. We define the intersection point here as point Z. In the next step, we'll focus on the small quadrilateral ZYTC. In this small quadrilateral, we have 1, 2, 3 right angles, therefore the fourth angle here must be also equal to 90 degrees. So we can relate to this quadrilateral ZYTC as a rectangle because it has 4 right angles. And we also note that the opposite sides of this rectangle must be equal to each other. That is to say YC equals to ZT. But YC is 3, therefore ZT must be also equal to 3 units in its length. Likewise, in the same rectangle ZYTC, side TC must be equal to the opposite side ZY. But TC is 3, therefore ZY must be also equal to 3 units in its length. As I already mentioned before, side GT is one straight line, and the length of this straight line GT is 7 units. The straight line GT equals to 7 units. So here GT minus GQ minus ZT, again GT minus GQ minus ZT equals to the missing side QZ. Repeat again, the missing side QZ in total equals to GT minus GQ minus ZT. So the missing side QZ equals to GT that is 7, minus GQ that is 3, minus ZT that is also 3. So the missing side QZ equals to 7 minus 3, that is actually 1. So the missing side QZ equals to 1 unit in its length. So we can argue that QZ, this is the missing side, that is equal to 1 unit in its length. Likewise, we have already found out that NY is one straight line, and the length of this straight line NY is 24 units. Here, NY equals to 24 units in its length. So NY minus NP minus ZY, repeat again, NY minus NP minus ZY equals to the missing side that is PZ. Repeat again, the missing side PZ must be equal to NY minus NP minus ZY. So the missing side PZ must be equal to NY that is 24, minus NP that is 3, minus ZY that is also 3. So in total PZ equals to 24 minus 3 is 24 minus 6, that is actually 18. So we found out that the missing side PZ equals to 18 units in its length. Got an idea that PZ equals to 18 units in its length. In the next step, we've already found out that GT is a straight line. The length of this straight line GT is 7 units. So if we focus on this side of the straight line GT at point Q, here the sum of the angles must be equal to 180 degrees according to the rule that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at this side of the straight line GT at point Q? We have this angle that is equal to 90 degrees plus the missing angle. In total they must be equal to 180 degrees. Therefore this missing angle must be equal to 90 degrees. So this angle equals to 90 degrees, this angle also equals to 90 degrees according to rule number 1. BC is one side of rectangle ABCD, therefore it is absolutely a straight line. If we focus on this side of the straight line DC at point Y, here the sum of the angles must be equal to 180 degrees according to the rule that I mentioned. So which angles we have at this side of the straight line DC at point Y? We have this angle that is equal to 90 degrees plus the missing angle in total must be equal to 180 degrees according to the rule that I mentioned. Therefore, this missing angle must be equal to 90 degrees. So we actually found out that inside quadrangle QKYZ, we have 1, 2, 3 angles, therefore the fourth angle must be also equal to 90 degrees. If we focus on the upper side of the straight line NY at point Z, the sum of the angles must be equal to 180 degrees according to the rule that I mentioned. So which angles we have at the upper side of NY at point Z? We have this angle that is equal to 90 degrees plus the missing angle. In total they must be equal to 180 degrees. Therefore the missing angle here must be equal to 90 degrees. So because of the fact that angle QZP, this angle equals to 90 degrees, it means that the green triangle QPZ is a right triangle. The green triangle QPZ is a right triangle. In the next step, I will copy the right green triangle QPZ in a new page, and we will implement the Pythagoras theorem on this right triangle QPZ. By PT is the relation for Pythagoras theorem. So actually, this is the right hand triangle QPZ that they copied from the original drawing. QP equals to 1 unit, PZ equals to 18 units, and this angle equals to 90 degrees. According to the Pythagoras theorem on this right triangle PQZ, we'll get that PQ square equals to QZ square plus PZ square. So PQ square equals to QZ square. QZ is 1, therefore QZ square is 1 square, that is 1, plus PZ square. PZ is 18, therefore PZ square is 18 square, that is 324. So PQ square equals to 324 plus 1 is 325. We take a root out of this equation, and we will get that PQ equals to the square root of 325. But 325 is 25 times 13. Here we can take 25 out of the root. The square root of 25 is 5, and inside the root we left only 13. So in conclusion, we found out that the distance between the centers of the two circles, that is to say QP, is equal to either 5 times square root of 13 units, so in terms of numbers, PQ equals to 18.03 units. And that is the answer to the question. In the next step, I'll summarize the lecture. So in this lecture, we found out the distance between the centers of those two circles, that is to say, the length of this line segment QP. In the drawing, we have rectangle ABCD, side AB equals to 7 units, side BC equals to 24 units. Inside this rectangle ABCD, we have those two circles. The center of this circle is 0 at point Q, the center of this circle is 0 at point P. Our mission is to find out the distance between the centers of those two circles, or in other words, to find out the length of this line segment QP. So first of all, because of the fact that ABCD is a rectangle, it means that all the 4 angles inside this rectangle must be right angles. In addition, we know that the opposite sides of a rectangle are equal to each other. That is to say, side AB equals to side DC, but AB is 7, therefore DC also must be equal to 7 units in its length. Likewise, according to the sum rule, side BC must be equal to the opposite side AD. But BC is 24, therefore AD must be also equal to 24 units in its length. In the next step, we implemented the Pythagoras theorem on the right triangle ABC. According to the Pythagoras theorem in the right triangle ABC, AC square equals to AB square plus BC square. So AC square, that is the square of the hypotenuse, equals to AB square. AB is 7, therefore AB square is 7 square, that is 49, plus BC square. BC is 24, therefore BC square is 24 square, that is 576. So in total, AC square equals to 49 plus 576 is 625. AC square equals to 625. We took out of this equation, and finally we found out that AC equals to the square root of 625, that is 25. So the length of the hypotenuse in the right triangle ABC, AC equals to 25 units. Then the right triangle ABC blocks this circle, while the right triangle CDA blocks this circle. So in the next step, we actually developed a general formula for the radius of any circle that is blocked by a right triangle. So triangle ABC is a right triangle, and it blocks this circle with radius x. So we developed a new formula that will help us to find out the radius of this circle that is x, only by knowing the side lengths of this right triangle ABC that blocks this circle. Here, side BC is tangent to this circle at point N. We join points O and N. The radius ON is known to point N, that is the point of tendency of tangent BC with this circle. Whenever we have a radius that is known to the point of tendency, then tangent BC will be perpendicular to the radius NO. That is to say, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. We define the point of tendency of tangent AB with this circle as M. OM is the radius of this circle that is known to point M. Therefore, according to rule number 1, this angle equals to 90 degrees, this angle also equals to 90 degrees. So inside quadrilateral OMBN, we have 1, 2, 3 rectangles, therefore the fourth angle must be also equal to 90 degrees. Therefore, we can relate to this quadrilateral OMBN as a rectangle because it has 4 rectangles. And you also note that the opposite sides of a rectangle are equal to each other. That is to say, ON equals to MB, but ON is x, therefore MB must be also equal to x. Likewise, according to the sum rule, OM equals to NB, but OM is x, therefore NB must be also equal to x. So I actually found out that quadrilateral OMBN is not a rectangle but a square. Why? Because all of its sides are equal to each other. Each side of this square is equal to x. Here AM equals to AB minus MB. That is to say, AM equals to AB, that is A, minus MB, that is X. So in total, AM equals to A minus X. Then we found out the length of this line segment and C, or CN. From the law, it is very easy to see that CN equals to CB minus NB. That is to say, CN equals to CB, that is B, minus NB, that is X. So in total, CN equals to B minus X, and then we found out that AM equals to A minus X. Then I presented to you rule number 2. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. We have the common external point P. From this common external point P, we have two tangents to the circle, tangent PA and tangent PB. According to this rule, rule number 2, PA equals to PB. You can implement rule number 2 in our drawing. Why? Because in our drawing, from the common external point A, we have two tangents to this circle, tangent AM and tangent AS. And according to rule number 2, they are equal to each other. That is to say, AM equals to AS. But AM is A minus X, therefore AS must be also equal to A minus X. In the next step, we focus on the common external point C. From the common external point C, we have two tangents to this circle, tangent CN and tangent CS. And according to rule number 2, they must be equal to each other. That is to say, CN equals to CS. But CN is B minus X, therefore CS must be also equal to B minus X. So the hypotenuse AC of the right triangle ABC, from one side it is equal to C according to our definition. From the other side, the hypotenuse AC equals to AS plus SC. So we can write here that the hypotenuse AC of the right triangle ABC equals to AS plus SC. AS is A minus X and SC is B minus X. So in total, C equals to A minus X plus B minus X. That is to say, C equals to A plus B minus X is minus 2X. So C in total equals to A plus B minus 2X. We added 2X to this equation and found out that C plus 2X equals to A plus B. We subtracted C from this equation and found out that 2X equals to A plus B minus C. We divided this equation by 2 and finally found out that X equals to A plus B minus C over 2. So actually we succeeded to develop a general formula for any circle, for the radius of any circle that is blocked by a right triangle. The radius of this circle X that is blocked by the right triangle ABC equals to A plus B minus C over 2. Now we can implement the new formula in our drawing. Why? Because in our drawing we have the right triangle ABC blocks this circle. We define the radius of this circle as R. We can find out the radius of this circle R by implementing the new rule in our drawing. The radius of this circle R that is blocked by the right triangle ABC must be equal to AB plus BC minus AC over 2. Repeat again, the radius of this circle R must be equal to AB plus BC minus AC over 2. AB is 7, BC is 24, minus AC that is 25 over 2. 7 plus 24 is 31, 31 minus 25 is 6, and 6 over 2 is 3. So we found out that the radius of this circle R equals to 3 units. Then we found out the radius of this circle by implementing the same formula in this circle. We define the radius of this circle as X. This circle is blocked by the right triangle CDA. So according to the new formula, the radius X of this circle must be equal to CD plus DA minus CA over 2. Repeat again. The radius of this circle X must be equal to CD plus DA minus CA over 2. CD is 7, DA is 24, minus CA that is 25 over 2. 7 plus 24 is 39, 39 minus 25 is 6, and 6 over 2 is 3. So we found out that the radius of this circle X also equals to 3 units in its length. Then we define the point of tendency of tangent BC with this circle as M. PM is the radius of this circle that is drawn to point M. Therefore, according to rule number 1, this angle equals to 90 degrees and this angle also equals to 90 degrees. We define the point of tendency of tangent AB with this circle as n. The radius Pn is known to point n, therefore according to rule number 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So inside quadrilateral Pn, Bm, you have 1, 2, 3 angles, therefore the fourth angle must be also equal to 90 degrees. So inside this quadrilateral Pn, Bm, we have 4 angles. Therefore, can relate to this quadrilateral Pn, Bm is a rectangle. We also know that the opposite sides of a rectangle are equal to each other. That is to say, Pn equals to Bm. But Pn is 3, therefore Bm must be also equal to 3. In the same rectangle, side Pm must be equal to the opposite side NB. But Pm is 3, therefore NB must be also equal to 3 units. So we found out that quadrilateral Bm is not a rectangle but a square. Why? Because all of its sides are equal to each other. Its side of this square is equal to 3 units. We repeated on the same process here. According to rule number 1, we get that QKDG is also a square. Each side of this square equals to 3 units. Then we extended the radius GQ by side line until it touches side BC at point T. GQ is the radius, and when you extend a straight line by side line, the result GT must be also a straight line, so GT is one straight line. In the big quadrilateral TCDG, we have 1, 2, 3 angles, therefore the fourth angle must be also equal to 90 degrees. So inside this quadrilateral, the big quadrilateral GDCT, we have 4 angles. And we also know that therefore can relate to this big quadrilateral GDCT as a rectangle. And you also know that the opposite sides of a rectangle are equal to each other. That is to say, GD equals to TC. But GD is 3, therefore TC must be also equal to 3 units in its length. According to the same rule, in the same rectangle, GT must be equal to DC. But DC is 7, therefore GT must be also equal to 7 units in its length. Then we extended the radius NP of this circle by side line until it touches side DC of the rectangle at point Y. And Y is one straight line. So, in this way, we created quadrilateral NBCY. In this quadrilateral NBCY, we have 1, 2, 3 angles. Therefore, the fourth angle must be also equal to 90 degrees. Therefore, inside this quadrilateral NYCB, we have 4 angles. Therefore, we can relate to this quadrilateral NBCY as a rectangle. And we also know that the opposite sides of this rectangle must be equal to each other. That is to say, NB equals to YC. But NB is 3, therefore YC must be also equal to 3 units in its length. According to the same rule, in the same rectangle, BC must be equal to NY. But BC is 24, therefore NY must be also equal to 24 units in its length. Here, we wrote down here that NY equals to 24 units in its length, and GT equals to 7 units in its length. So, we defined the intersection point here as point Z. Then we focus on the small quadrilateral ZYTC. This quadrilateral, we have 1, 2, 3 angles. Therefore, this fourth angle must be also equal to 90 degrees. So inside this the small quadrilateral ZYCT, we have 4 angles. Therefore, we can relate to this quadrilateral as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, TC equals to ZY. But TC is 3, therefore ZY must be also equal to 3. Likewise, according to the same rule, in the same small rectangle, YC equals to ZT. But YC is 3, therefore ZT must be also equal to 3 units in its length. So what is the length of this line segment QZ? QZ equals to GT. Again, QZ equals to GT minus GQ minus ZT. Again, QZ equals to GT minus GQ minus ZT. Repeat again. QZ equals to GT minus GQ minus ZT. So QZ equals to GT, that is 7, minus GQ, that is 3, minus ZT, that is 3. So in total, QZ equals to 7 minus 3 minus 3, that is 1. So found out that the missing line segment QZ equals to 1 unit in its length. Likewise, we found out the length of this line segment PZ. From the knowing, it's very easy. First of all, NY is one straight line that is equal to 24 units. Yeah, we found out that NY equals to 24 units in its length. So NY minus NP minus ZY equals to the missing side PZ. I repeat again. Again, the missing side PZ equals to NY minus NP minus ZY. So PZ, the missing side, equals to NY, that is 24, minus NP, that is 3, minus YZ, that is also 3. So in total, PZ equals to 24 minus 3 is 24 minus 6, that is 18. So we found out that the missing side here, PZ equals to 18 units in length, and we already found out that QZ equals to 1 unit in length. Then we have already found out that GT is one straight line that is equal to 7 units in its length. If you focus on this side of the straight line GT point Q, the sum of the angles must be equal to 180 degrees according to the rule that the sum of the angles from one side of a straight line is equal to 180 degrees. So which angles we have at this side of the straight line GT point Q? We have this angle that is equal to 90 degrees plus the missing angle in total must be equal to 180 degrees. Therefore, this missing angle must be equal to 90 degrees. We have already found out that this angle equals to 90 degrees according to rule number 1. So DC is one side of rectangle ABCD, therefore it is absolutely a straight line. If we focus on this side of the straight line DC at point Y, the sum of the angles must be equal to 180 degrees according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have this side of this point Y? We have this angle that is equal to 90 degrees plus the missing angle in total that must be equal to 180 degrees. Therefore, this missing angle must be equal to 90 degrees. So I actually found out that inside quadrilateral there are QK, YZ. Inside this small quadrilateral QK, YZ, we have 1, 2, 3 angles. Therefore, the fourth angle here must be equal to 90 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Then we focus on the upper side of the straight line NY at point Z. On the upper side of the straight line NY at point Z, the sum of the angles must be equal to 180 degrees. So which angles we have at the upper side of NY at point Z? We have this angle that is equal to 90 degrees, plus the missing angle in total, they must be equal to 180 degrees. Therefore, this missing angle must be equal to 90 degrees. And because of the fact that angle QZP equals to 90 degrees, it means that the green triangle QPZ is the right angle. So I copied the right green triangle QPZ in a new page and we implemented the Pythagoras theorem on this green right triangle QPZ. This is the right triangle QPZ that I copied from the original drawing. Side QP equals to 1 unit, PZ equals to 18 units, and this angle equals to 90 degrees according to rule number 2. In this right triangle QPZ, according to the Pythagoras theorem, PQ squared equals to ZQ squared plus PZ squared. So PQ squared equals to QZ squared. QZ is 1, therefore QZ squared is 1 squared plus PZ squared. PZ is 18, therefore PZ squared is 18 squared, that is 324. So PQ squared equals to 1 plus 324 is 325. So PQ squared equals to 325. We took a root out of this equation and found out that PQ equals to the square root of 325. But 325 is 25 times 13. So we can take 25 out of the root. The square root of 25 is 5. So inside the root we left only with 13. So in conclusion we found out that the distance between the centers of those two circles QP, it is equal to either 5 times square root of 13 units, or in terms of numbers, QP equals to 18.03 units. Okay, thank you very much.